function, and especially at the response function, and that we derive some correction terms, which are very important if you want to understand experiments. You need really to take care of the correction terms. Today I want to discuss some specific systems, and these are here in order of complexity, starting with the perfect magnet, then I will go over to add disorder, and you have disordered magnet, and then if I have time, I will add some frustration and discuss a little bit the typical spin class. Now, for some reason, maybe a reason of time, I focus on Friday, I focus on autocorrelation of the response function, which are, when you plug in here, are equal to 0. But however, we know all this stuff also for space-time correlation and space-time response functions, and I will today discuss a little bit more detail when discussing different models. So for this quantity, we now not only have a scaling function of T over S, but it also depends on the space. So we have here the distance between the different points divided by the typical length scale, which is L to the power S. And I remind you, and we have similar order for the response function, and I remind you that I will discuss the only cases where the growth law is given by a polar growth. Okay. We will see whether this fulfills these more complex systems, or more complex systems later. Okay, now I insisted Friday that we can do a lot by forming exact models, and therefore I added a couple of slides to give you at least a taste of what kind of exact model we're looking into and what kind of results we obtain. So one of all-time favorites is of course the eigenmodel, and if you go to one-dimensional, you can solve it in all its beauty and also for dynamics. It's not really an easy exercise. To some extent, Paul Glauber solved it in his original 1963 paper. However, the complete solution is due to Godwin and Glück and a little bit on to Zanetti, who did in parallel similar work. Now, you see here popping up something which you all know, because we discussed it extensively in the first week of this lecture. You have here a master equation. And I really want to insist that in this field, all the techniques which we have discussed in the last 2 weeks are used. We are solving exactly probable models, we are doing field theory, we are doing numerical simulations. Any method you can imagine is used in this field, depending on what kind of model you're looking at. Okay, so for the eigenmodels, they are simple. We have here the probability, the given spin configuration is observed at time t, and we have here the time change in function of time. That's given by two contributions. One is the gain term, where the one spin is flipped. So in the original configuration, there's a minus sigma j, and then minus sigma j is flipped to sigma j. That's the gain term, and then the loss term. And you're solving this kind of equation exactly like Sid discussed that using the generating functions, using Laplace transform, Fourier transform, all these methods you can use here, and then solve it. And these are here the rates. And when you do that, you can then compute really everything. So for example, for the autocorrelation, auto-response function, you have this kind of results. And when you look into this a little bit closer, you see that exactly this kind of scaling functions. S to some exponent multiplied with the correlation function is only 0, multiplied by a scaling function only kind of t divided by s, and also for the response function, you have this kind of scaling.
Michel?
Yeah?
Can you say something about these rates? I mean, is that, you already talked about this before, the rate, the form of the rate, W?
No, I didn't discuss that before. I do not really want to enter the details of this model. Let me give you a feeling, a taste of what kind of system you're looking into.
But that's an input to the model?
Yes, that is the model.
That's not.
This is the dynamic, the Glauber eigenmodel. The dynamic part of the decision of the model.
Okay, that's W definition. Okay. And also the form, these scaling forms, these are asymptotic statements, or these are? These are statements for when all times are large compared to any microscopic time scale. So in a microscopic time scale would be the typical time to fit one spin. And this is within your phase, right? Or this is coarsening?
Again?
You're talking about coarsening, or are you talking about being deep within some glassy phase and asking about?
It doesn't matter. For example, here for the Ising model, we don't have coarsening in strict sense. The phase transition at t equals 0. If you want to be a little bit large with what you understand of phase transition. So this is in fact critical, special critical system, where coarsening and phase transition features are appearing at the same moment. It doesn't matter. In this kind of scaling function, you observe the glassy system, in phase ordering, in critical systems. It's very general.
I'm a bit confused about the singularity and equal.
That's an exact result of medicine. This is an exact result. It comes out of the solving. What does it mean?
The correlation function diverges with the times are equal.
That is the exact result in the positive graph.
Well, that's why I was asking this professor. Is this true for very short time?
Well, no. T minus n, those are large times.
There's probably a short time cutoff, microscopic time cutoff.
Yes, this is microscopic. That's true. Sorry, absolutely. Yeah, that is. Yeah, indeed. Thank you. And what I said wasn't correct. So we have that this condition here. This condition here. And we have the time difference, and I explained that in more detail on Friday, and sorry for the confusion, but this is also large compared to maximum testing. Yeah, thank you.
And this is at zero temperature, right?
This is at zero temperature. Of course, we can discuss on treatment, Claude and Jean-Marc have done that, also the behavior at higher temperatures, then has a crossover from this kind of scaling to finite size scaling behavior to equilibrium scaling. Another model which is one of the old-time favorites is the spherical model. I introduced that briefly on Friday. So here we have the methodology similar to the Ising model, only that these are now real numbers. And we have the constraint that the square of these real numbers from the all lattice sides is the number of lattice sides. Now, how to solve that? Well, usually one way of doing it is to write down the Long-High equation where a parameter lambda is appearing here. And this lambda is Lagrange multiplier, which enforces the spherical constraint. So it is the spherical constraint which makes this model non-trivial. And we can solve that with usual methods, Fourier transform, etc., etc. And when you do that, again, you have only one negative result. You can compute, for example, the response function. And again, we have a scaling behavior similar to what I postulated. So this is really all this. Our knowledge about alien systems, to a large extent, relies on exactly solvable cases. And I cannot stress enough how useful it is, even when these are toy models, they are not really realistic models. Still, they give very important insight into what is possible, what kind of scaling behavior one can do. And I should mention that the spherical model here is, of course, a thermodynamic model, but people also have looked at the spherical spin glass. And this has been done for Kubiangelo and Dean, for example, and one can also solve there everything in all its details. This more or less only was something which I did over the weekend in order to show you that indeed we can compute a lot in exactly sort of model, and from this result we can derive that this is the typical scaling behavior in a system. Okay, now let me come to the main part of my talk. I want to discuss these three different systems. A perfect magnet, a disordered magnet, a spin glass. And here is a time evolution. So what I'm doing here, I'm preparing the system always, let's say, at very high temperatures, and then I'm punching it down to low temperature, below or at the critical point. These are all below the critical point, and I measure how, well, basically how the system evolves in function of time. And you see here the formation of domains. So again, Kip already showed similar pictures and movies in his talk on 2 weeks ago. And you see these domains grow as a function of time. So we have here this domain growth. Now, when you add this order, we observe that the domains are much smaller. At the same time, okay, after the quench, the domains are much smaller and the increase is much slower. What is happening here is that due to the disorder, the domain modes are pinned, so they are not moving so freely anymore, and this then yields to smaller domains. Yeah, okay?
Your left column there, that's non-conserved order parameter?
Yes. We only discuss here non-conserved order parameter. We also did not we. Other people did conserved order parameter. I will not discuss that today.
How are you putting in the disorder?
I will come to that now. because this is exactly the important point. There are different ways of doing it. I will discuss what in a moment. Okay, now for spin glasses, obviously, well, what is happening here, no one knows. There are clearly no simple domains which are forming. It's a much more complex situation. And yeah, spin glasses start to be already very complicated systems. And I will, if I have time, briefly discuss that here. Okay, you already saw, alright, this is what's my setting. I start at very high temperature. I quench my system down to low temperature. I will here discuss only phase objects. I will not discuss the quenching the critical point. A lot has been done for the critical point, and then using field theoretical methods along the lines Nicola has discussed in the last lectures. And a lot is known about the critical point here, but I will here focus on the phase objects. So we have here, what is important here, we have competition between two different equilibrium states, where the percent is negative domain type or positive domain type. And because of this competition, we observe this formation of domains. To give you a sketch of the free energy here, that would be the free energy as a preparation. We have one sitting in one minimum, the free energy at high temperature, and then we're quenching it down. Then we have the two equivalent minima corresponding to the two equilibrium states, and the system then has to choose, or well, it's out of equilibrium, and basically it has competition between these two different states. And for an infinite system, the system never relaxes to equilibrium. Okay, and you already saw this again. Also, so we have the information of domains due to this competition, and the slow degrees of freedom are domain walls, which are moving through the system, and the growth law is then the power law, where for non-conserved dynamics C is equal to E. So this is what you all saw, and now let me discuss a little bit some numerical data. In fact, I also want in this class to give you a taste of a theoretical approach which we have developed, which is, I think, by far the most successful theoretical approach to describe not derived scaling functions, but it's also an approach which we do not yet fully know whether it is applicable to more complex systems. So, talking about the Ising model, you all know the Ising model here, and here is the permanent magnetization. So you recall the setting, that we are quenching down the system in a magnetic field, and after the waiting time, we take away the magnetic field, and then measure the relaxation of our sample in function of time. And here, if I plot here the time difference, t minus s, you see the different curves are different, we are able to behave. Maybe for those of you who are interested in numerical simulations, how do we compute this kind of response? So naively, if I would, for example, add a homogeneous magnetic field, what we would observe then is that one would really favor one of these equilibrium states. For example, let's say black spin corresponds to spin pointing up. We have magnetic field pointing up, then very rapidly all this would basically be black. The system would go to equilibrium very rapidly when we apply a homogeneous magnetic field. So what Baraha has proposed some years ago is not to add a homogeneous magnetic field, but to add a random field. A weak random field on every lattice side, and the sign of the magnetic field is pointing up and down randomly. So when you do that, you can then compute this response here, and this is basically then the response of interfaces to this magnetic field. Which is exactly what we want to look into. We can see whether we observe dynamic scaling, and here I have plotted the H part. So I have subtracted along the line I scheduled Friday the correction terms, and then we see here by plugging in the exponent which we all discovered on Friday, A is 1 over Z, we do observe a nice data collapse in 2 dimensions, in 3 dimensions, and these for different waiting times. So we do observe dynamic scaling in the Ising model, and if we take care of the correction terms. Yeah?
If you apply a random field, wouldn't your coarsening be completely different?
It's a very weak. We are still linear response regime. It's a very weak random field. But yeah, if you would take what we're doing here is that we cut the random field after some time. Okay? We do not keep it all the time. So if you would keep a random field all the time, at some point you would basically destroy your order. Yeah, the random field Ising model doesn't have phase notation dimensions. But we have linear response regime, and that works. Okay, so you can also look at the correlation function. Again, the exponents we discussed on Friday, and here the correlation function has beautiful scaling behavior. So we do observe all this kind of scaling, which I discussed in detail. Yeah.
Sorry, I didn't understand. If you don't put a random magnetic field at all, what happens?
Well, then you can't compute a response function. You need to disturb the system in order to compute a response function.
Okay. So you put, and you after that you turn off.
Okay, so what is a possibility to describe this kind of system? So this approach is sometimes called the theory of global scaling invariance, and I want to sketch it here and also give you some insight into what are its strengths and what might be its weaknesses. So the starting point is non-quadratic, and we heard this in many, for example, Nicholas class. We have non-linear equation for non-constant order parameter. This is model A dynamic. So we have this kind of equation here. This is the noise. We assume Gaussian white noise, and this is V is the Ginzburg-Lambda potential. So this is standard description of this kind of systems. And as we are dealing here with phase ordering, the first thing one can tell is, for example, well, from the relation viewpoint, being in the broken low temperature phase is the same as being at zero temperature, because the fixed point is zero temperature fixed point. So the first thing one might want to do is, okay, let's say we want to look at the noiseless equation, because noise only enters, the temperature only enters through the noise term. So we might first get rid of the noise term and then see what we can do. So we first look at the noiseless term, and then we do a much more serious approximation. I will first consider the free field case. So we don't have any potential. Yeah?
Why is there a Laplacian term?
What is Laplacian?
Is the delta phi in the...
Yes, sure.
That should come out from the Ginzburg-Lambda function derivative, right? Yes. So mu does not contain grad square.
No. Mu is the potential. The on-site potential.
Okay.
Usually the mobility is put next to the Laplacian that's here on the left-hand side.
Oh, well, this is the inverse.
Yeah, but now it hits everything else too.
Yes. So, I can do that.
Yeah. And it's 1 over the mobility of the loop.
Yeah.
It's a direct.
So, what you might call nu is 1 over 2n. The only thing is happening that there are some here, this prefactor is changed.
Okay.
Okay.
There should be m in front of t, right?
M in front of
T. Unannoyed.
there is a diffusion constant in front of T usually.
Well, that m.
No.
It's on the other
Sorry.
side.
This one?
That m, yeah, that m should appear in front of t.
No.
No. Because of that rescaling, precisely because it's in the left hand side.
Because it is scaling to the left hand side. Okay, so when you do all this stuff here, in this case t equals 0, well, you end up with something you all know. This is diffusion or Schrödinger equation. Schrödinger equation, because when you replace time by complex time, this is a well-known Schrödinger equation. So let's discuss the Schrödinger equation. Well, you obviously know everything about the Schrödinger equation. Do you know all the symmetries of the Schrödinger equation? We all know the Schrödinger equation is invariant on the global scale transformation. So we multiply space by some constant, we have to multiply time by the constant to the square, and then we observe that any solution of the Schrödinger equation is given by a solution without this rescaling multiplied by the scale factor of some exponent. This is the starting point for global scale invariance, and it's really can very nicely be observed. Now, this is not the only symmetry the free Schrödinger equation has. It has a much broader symmetry class, and This is observed when you now allow V not to be constant, but to depend on space and time. We are talking here about local space and time dependent scaling, and when you do that, you obtain something which is called the Schrödinger invariance. This has been studied to some extent, or in fact, extensively by Niederland Hagen in the early 70s. So what are the symmetry elements of the three Schrödinger equation? In fact, there are quite a few. There's the global scale transformation, and all can be written in this very compact form. So we have the global scale transformation, we have time translation, we have spatial translation, we have Galilei transformation, and we have something which is called the special Schrödinger transformation, which is given by this very strange behavior, and alpha, beta, gamma, and delta are constants which have to fulfill this relation. So all these different symmetries are map a solution of the Schrödinger equation to another solution of the Schrödinger equation.
I do understand the first one, but not the last one. How should I think of it?
This is basically conformal transformation in time.
The different geometry.
Yes.
So the time we showed in the previous thing did not scale as space, right? So why is that the time swinging the conformal transformation the same as spatial?
For this year?
Yeah, because
Plug it in?
wasn't the time scaling like P square scales as
This is global scale transformation. Now I'll allow B to depend on space and time. And you can, from this relation, you can derive how B looks like.
But is that global one should be a special case included into these?
exactly? That's what I'm thinking.
These are different symmetry elements. Okay? All these symmetries together form a group, which leads to Schrödinger, which transform one solution of Schrödinger equation to another solution of Schrödinger equation.
Conformal invariance also includes the global transformation, right?
No, there's no conformal invariance. This is a special transformation. Separate. This is not. It does not. The special Schrödinger transformation does not contain the global scale transformation. It's different to that. Okay. Now we are discussing here non-equilibrium systems. So we at some point have to get rid of time of invariance. So what you should maybe keep in mind, and we're not discussing in detail, that from all this list here we have to get rid of time of invariance because that is not fulfilled out of equilibrium. Okay, so this transformation from a group, from a Lie group, and we can set up in a Lie algebra. You all know this to some extent because you did that in quantum mechanics when you discussed angular momentum, when you discussed rotations. You all have dealt with Lie groups, even though they weren't called Lie group in your class, you dealt with Lie groups. And you all know that the angular momentum is specific algebra. So Lx, Ly is epsilon x, y, j, epsilon x, y, z, and c. So there's a specific algebra here. So it's exactly the same here. So we can write down the generators, and these generators have to fulfill a specific algebra. I will absolutely not enter the details here. So these are but I will discuss how these generators work. So these are the general, how to write down the generators. And this is the corresponding algebra. And again, this is exactly along the same line you saw in your quantum mechanics classes when discussing angular momentum. Nothing else. So what I want to discuss in the following is how does this generators transform space and time? At least for different cases. Now this, I know this picture from an article by Haya Hinrichsen, who very nicely illustrates what is happening here. So for example, this here is the time derivative, and I'm claiming that it generates translation in time. In order to see that, what we have to do, we have to exponentiate this operator. And when you do that and then apply the some function which depends on time and space, you observe that this is nothing else than t minus tau, so a shift in time. So this corresponds to this here. You're seeing here space, here's time, and my whole lattice, my whole lattice is space-time lattice, space-time. Yeah. Space-time lattice is shifted in time. For sure you have seen the following. This is translation in space, and I'm claiming that all of you have seen this at least in the homework. So when you have the space derivative, you exponentiate it, apply it to some function, you see that we have a shift in space, and this is exactly what is illustrated by this figure here, that we have a shift in R direction. You can also look at this more complex operator. This is the operator for the global scaling, for the anisotropic dilatation, which one sometimes call it. So we have here a different scaling in space and time direction, and you see here a factor 1.5 popping up, which makes this different scaling. Again, we exponentiate it, we see that, okay, t gets a factor of b, so t over b, and r gets a factor of b to the square root of b, the factor of square root of b. So we see here, and this corresponds to this guy here, that space and time are rescaled differently. So this anisotropic scaling is really at the heart of the non-equilibrium system. And finally, the last one I want to illustrate is the Galilei transformation. Again, we have that really starts to be a more very complicated expression, but still you can exponentiate it and you can see how it works. And see this guy here, and we see here what's happening is that the R component, space component, is shifted by minus t times time. And C is from velocity. And you can also then discuss the other remaining narrators. So we understand the full symmetry group of the Schrödinger equation quite well nowadays. And what I'm claiming is that we can exploit the symmetry in order to compute scaling functions. So this is not really obvious, and in fact the first sentence, if you read it, you might think, okay, that's the end of the story. We already in the very first class in this summer school, Roy Sear showed that when you have noise, thermal noise, Galilei invariant is broken. End of the story, I might say. That means that, okay, we have these nice symmetries when t is equal to 0, then we plug in temperature, everything is broken, forget it, end of the story. Okay? Well, luckily it's not the end of the story. There's a way of still dealing with it, but it's not a straightforward one. So the starting point is exactly what Nicholas did in his very first lecture. He set up a field theory for it. So we're starting from the model A dynamics, we can set up the field theory. There's nothing here you don't know, so we end up with the partition function. Here is the action, and I call this the Gantt-Dominici. You can also call it Martin-Figueroa, wherever, what side of the Atlantic you're coming. So, and this action has two terms. This is a term which Nicholas discussed in his lectures. Then I have here one term which at least I have not completely seen in Nicholas' lectures up to now. This term here comes from the initial preparation of the system. Now we are out of equilibrium, and the initial preparation of the system is of importance. So Nicholas was discussing steady state, and in steady state this term will not enter. However, we are not in steady state, we are looking at the relaxation of the system, therefore we need to include the initial preparation of the system. And this guy here is coming from the thermal noise. Okay? But with this small modification, exactly what you find in Nicholas' lecture notes, so we know how to deal with that. And then the question is, okay, can we do something with that? So the correlation function is given by phi times phi, the response function is given by phi times phi tilde, and this is also why phi tilde is sometimes called the response field, because it answers expressions to the response function. Okay, so any expectation value, again, is given by this path integral here with the given action. Now, what I'm claiming is that we can split all this in a very good way by separating the deterministic part from the noise part. And noise, I mean noise, thermal noise, and I mean noise in the preparation. So I will not only consider the expectation value with respect to the full action, but also with respect to the deterministic action. And then there's a theorem, which I'm not sure what's the name in condensed matter, but in high energy field it's called the Bachmann superselection rule. I think it's the same, isn't it? Which claims that when you're doing this kind of average for phi and phi tilde with respect to deterministic action, only those terms survive who have as many phi as phi tilde.
Because percentage.
Yes, absolutely. So you have only those terms are different from 0 when you have as many phi and phi tilde. And then we use that. So let's look at the response function first. So the response function, we can have this term here. And now instead of making the average with respect to the full action, I make the average with respect to the deterministic action, which means I have here now the average with phi times phi tilde times the exponential of the part of the action which comes from the noise. Then I can expand it, of course, to the power in phi tilde. And when I do that, you see, oops, the only term surviving is the first one, 1. Because 1 plus phi tilde, then we already have phi times phi tilde square, this is 0, due to the Bachmann superselection rule. So you see here that the average with respect to the full action is the same as the average with respect to the deterministic action.
It's only true if you don't have quantitative noise, right?
Yes. I put this kind of detail on the
Sorry.
But for our system, we are here, this is not true.
What was the question?
It's only true when there is no multiplicative noise.
Then KD is 5.
So you see here for phase ordering systems where it is true that the response function at final temperature should be the same as the response function at 0 temperature without any noise. This is a very strong result because it allows us to determine if you know this, we know that for any temperature. Okay. Well, we have this rule here, this theorem, okay? And if you now compute phi tilde, and then we have here some action, which is only a function of phi tilde, you can expand this. You can always expand the exponential. And this starts with 1 plus some constant phi tilde plus phi tilde square, etc. You see already the phi tilde here is a phi times phi tilde square, which is 0. Phi tilde to the cube is 0. Phi tilde to the 4 is 0. So the only term contributing which is different from 0 is which comes from the 1. Okay. Now, this part here is a whole lecture, and I will therefore only give the results. So what we can do, we can go back to our noiseless deterministic equation. We can exploit the symmetries, the Fuchs-Schrödinger group, and then we can see what we learned for the response function. And what we can show is that when we apply this generator to the response function, we end up with an explicit prediction how the response function should look like. This is a model-independent calculation. And the only thing which is not fixed here are the exponents. The function dependent of all the variables, space and time is fixed. This is a very strong result. Of course, we have to see whether this works for any system. We can do, but this more work, do a similar thing for the correlation function. We can also here expand the exponential. You can see we have here phi. So obviously the term contributing to the correlation function will be a phi tilde. 1 second. A phi tilde. So we have to compute a 4-point response function at t equals 0 in order to obtain the correlation function of final temperature.
Is this true even if the noise and the dissipation is not related by fluctuation?
Yes.
So there's no need, the dynamic should be equilibrium.
You can do the same for extreme dynamics.
I think, okay, that's not a necessity for the Bachmann selection.
No, the Bachmann selection book does not even know about this statement.
So I missed something probably. So after you do that averaging, you're relating this theory to the original theory which had all the symmetries, including time translational symmetry, right?
Absolutely.
So why do I see...
No. And then I have to get rid of the time translation symmetry. If I would keep time translation symmetry, you would end up with a response function where this term is not there.
Exactly.
And this is something which obviously you know is valid, because it's nothing that's fusion.
So which step did I have to put in where I am breaking time?
We're looking at the subgroup of the Schrödinger group where we have removed time translation variance.
Subgroup of the shortened group. Okay.
And this then yields this additional term here. Okay, so this was the sketch of the theory. Now let's see whether this works. Now we did a lot of tests of synthesis in order to see whether the co-construction makes sense. So we looked at linear long-drag equations. Of course we can't solve them exactly, but this is really a test case to see whether this is going back to the symmetry group of noiseless theory allows us really to make all this construction. And in any case which we discussed, and I think nowadays the consensus that this really works for any linear long-drag equation, we see that the expression which I just gave you are in agreement with the exact expression. So our construction is valid, is correct. So the big question mark is, what do we have for, let's say, more realistic system? But obviously we are not dealing with a linear long-drag equation, but with a non-linear long-drag equation.
Why would you doubt your concept?
Well, we didn't doubt it, but lots of other people did. So therefore we really make a very systematic study over a couple of years in order to look at all the cases.
The Schrödinger group was for potential. It has to be free Schrödinger group.
I was going to see.
Yeah, and I forgot something to mention. What I just get was equal to. We have the full theory for any value of z. Okay? So there, in fact, even the symmetry elements were not known before. So we have the full, we can do the construct for any value of z. And you see here values of z which is 0 and 2, 4, and all the other cases. So from the Schrödinger point of view, I think not so surprising, but then we have to generalize that to for different values of dynamic exponents.
So the spatial structure in the original theory, of course, it was homogeneous, right? But we know,
I assume that the spatial structure remains homogeneous.
but that's very because in the coarsening we
Oh no, that doesn't mean that by homogeneous. I don't have surfaces and stuff like that. What does that mean by homogeneous? There's no surface in space, for example.
But in the coarsening dynamics you will gather surface terms, right?
Yeah, but that's okay. That's no problem.
Sorry if I missed it, but can you elaborate a little more on how you test if these Lagrange equations are good? Like what's your criterion exactly?
What we did, we solved the linear long-drag equation exactly for the different cases. It can be done with more or less work. In fact, here it's less work, here it is more work. So you depend on what model you're looking into. And then we make our construction, so we write down the noiseless theory, we determine the generator of the symmetry element, we use this in order to compute our response function and correlation function, and then we are comparing the scaling functions we obtain from the theoretical approach with the exact scaling function we obtain by solving linear equations.
Michel, so the statement on the previous slide about temperature dependence, that's true only for linear response, right?
I have always a linear response. There is no theory out there which works out beyond linear response. This is really one of the big question marks. One of the things to do in future to see how we can proceed. It's not even sure how we can proceed if you're going beyond linear response.
The system can be far from equilibrium, but it's it's relaxing. It has an equilibrium state to relax it.
Steady state. Not need to be in equilibrium state, must be a steady state. So we can do similar studies all of our systems or reaction fusion models, which not relax to an equilibrium steady state, but non-equilibrium steady state. So it must be a steady state We must select this one thing to well-defined steady state.
I'm still confused a little bit. So if you're quenching the system, suppose I do this experiment, I quench it many times, and I different temperature, quench to. I expect my starting system to, my system that it goes to have different sorts of homogeneity, right? Inhomogeneity of the person. Why can't I see that in your RTS?
But the scaling function should not depend on that. Why should the scaling function depend on that?
Because the scaling function should tell me how the coarsening is happening.
Yes, but it will be for any experiment, it will be the same way. Only the... Yeah. And we are in time regime where this doesn't matter anymore.
So this is for a linear case?
This is
the statement.
Our theory. That's the statement.
So,
and we
for which Langevin equation?
Any which
okay. The symmetry element. Okay. Again, we know that it works. The whole construction perfectly works. It is correct for linear algebra equation. For nonlinear algebra equation, it already starts to be very difficult to come up with symmetry elements. So neither for the Schrödinger equation already did that to some extent. It came up with some potential where it can really show that the symmetry elements are the same or what the difference is to without the potential. We do not have a general proof that it works for a non-P-field theory. That's exactly why in the following we discuss numerical data and see whether when you compare it to numerical data, whether this gives indication that this could be valid or not. We do not have a proof.
But what I'm asking is, if you take a non-trivial Langevin equation that satisfies your symmetries, is the claim that literally this form will hold, or it's just this, it'll be this Gaussian will be replaced by some other function of R squared over T, or what is the? How will this be modified if at all if you go to a non-trivial Langevin equation?
Well, a non-trivial Langevin equation will immediately change for a properly dynamic exponent.
No, okay, fine. But the exponent you have here free, Z, A, but the actual form of the function.
D is important. Because if you end up with if you're now going for a system with different Z, you end up with a fractional differential equation. And we made some progress in order to understand how this changed everything, but we are far from knowing it. And to be on the safe side, I would claim that right now, for a nonlinear differential equation, all this is an educated guess that it works without any proof. We have that means showing the following: for a non-trivial system, we do observe an agreement between numerical data, but there's no mathematical proof right now. This is too involved.
But do you think like a Gaussian will change, or will it still be Gaussian like what I mean?
This part here?
Yeah.
It will change.
Do you think it might change?
Well, for example, going to critical point, you know that it changes.
Okay.
But again, this is where we progress. Okay, so let's now do the comparison. You saw this numerical data, and the red curve are the theory curve, and the only fitting parameter is the overall amplitude because the exponents are known. Okay, and let's judge it by yourself. And this is really a non-trivial result because, as Leo pointed out, it's absolutely non-clear why this should work when we add against Pocklanda potential. It's really a control test. Now, if you would ask me whether this is exact or whether only a very good numerical, would not call it fit, a very good description of numerical data, I would right now claim it's not exact, because we do not yet know how to deal with nonlinearities. But obviously, the data fit it very, very nicely. Yeah?
The numerical data, is that for the Ising model? Or
this is our Ising model. We did Yankee did Potts model with the same result. XY model has been done. There are a lot of data out there that people look at.
Right, but the theory is rotationally symmetric, so I wonder about the lattice asymmetry.
Absolutely.
That was needed.
So we looked also at the space-time response, but this comes into account. And in fact, let me point out that there's a similar result here. This is only for convenience of showing an integration order in space, but it's still different. Now the lattice asymmetry comes into this non-universal factor M. This depends on what direction we're going. Diagonal direction along the lattice. We look into that, and this really changes when you're looking into correlation along an axis or a diagonal direction. This non-universal factor changes. It enters here. Okay, but this is again the space-time response, and we have a similar behavior. Good result. In fact, I think one of the nicest results that we have. And we can look at the correlation function, and there's a small deviation here, but this obviously comes from the fact that we know that for the correlation function, because we have this plateau before going to the aging regime, that this part here does not really scale, even though it looks like that, does not really scale. So we did expect this deviation, and by construction, this here goes to the magnetization square at t equals 0. So this is consistent with what we expected. And as I already mentioned, this has been also verified in many other systems, direct diffusion models, in pulse model, in XY models. The people looked in quite a few and have the same similar overall agreement between the theoretical approach and the numerical data. Again, do I think it's exact? No. Do I think it's an extremely good approximation? Yes. And as far as I know, it's the only known way of deriving scaling functions in a model-independent way. The only thing which you have to plug in are the exponents. The function dependence is given. Okay, now.
Sorry. From a coarse-grained point of view, shouldn't we expect that outside from the critical regime, at very long distance and very long times, we should. I guess that the theory should behave like a Gaussian theory. No, I am wrong.
Like a Gaussian theory? Why?
No, at least at the equilibrium there is this. When you approach the coexistent limit, there are some paper. I should look at the reference. I don't know how to.
But we are in a specific regime here, okay? Yeah. We are much larger than the microscopic time scale, much shorter than the equilibration time.
Non-linearities are still relevant. This is not out there where things, because they never reach an equilibrium. So we are not going to because of funny initial conditions. If you just went from the disordered into the disordered phase, from the ordered into the ordered phase, and in the Goldstone models, then everything relaxes fast exponentially, and then you get to a Gaussian theory. But because we're crossing the singularity here in the initial conditions at high temperature, we're ending in the low temperatures. You never really get there. So the non-linearities are always missed.
Okay. But the comparison between your theory and the numerical data is also done for a Gaussian theory?
Well, numerical data is Monte Carlo simulations.
It's Monte Carlo simulations.
Monte Carlo.
So it's a full model, has all the non-linearities, has all the wow.
So the statement magically somehow the non-linearities affect the exponents, but not really so much the scaling function, and of course no one really understands this, but that's the statement, I think.
Yeah, that's it. Yeah.
Now, I'm naive enough to like to think about coarsening in terms of interface dynamics. Is that buried somehow in
interface dynamics? This is exactly the picture which we have here. Yes,
it is.
So I'm thinking about using canherias and stuff like that without having the noise.
Yeah.
This is something that we need to do. We have done. This is something which we always discuss, always with Ben, and we discuss this. But we need to look into that. Yeah.
Michel? Where do the exponents come from?
The exponents I discussed it on Friday. The exponent, not on Friday. The exponent A, for example. Okay. The exponents here. The exponents 1/2 here come from the interface dynamics. The 30 degree of freedom are the moving interfaces. That's what I discussed on Friday.
It comes from the theory, or you can plug it in extra?
It is not from our theory. We do not know any. We do not know a way right now how to compute the exponents. We can discuss that in private, but let me only mention that right now there's a completely new approach using string theory, where people are mapping this to a gravity theory, non-trivial background, and there might be some hope that this might give a way of classifying the dynamic universality class and therefore classifying exponents. But this is a long story. We are just starting to go along that direction.
Once you have a scaling function and you fix that scaling function by putting in the asymptotic exponents, which are the values very close to the degree point, for a fixed point of the RG, if you go away from well, my question would be there are corrections to scaling exponents.
Yeah.
And you seem to say that the corrections to scaling exponents are model independent.
But we're talking about, not sure, okay, I'm quite confused.
Your scaling function is a deviation from the asymptotic power law behavior.
Yeah.
So your scaling function contains the correction to scaling exponents.
Yeah.
And your statement would then amount to saying that the correction to scaling exponents are super universal. They don't depend on features of the model.
Yeah. Give me 5 minutes, and we can come to this other ferromagnet, and we can discuss super universality. I will for sure not discuss spin classes today for the 7 minutes left, but let me discuss the donut magnet. Okay, so the donut magnet, what is happening now is that we have, for the only of the Wheeler's disorder, and this is the case I will discuss here, is that we have now couplets which are have not the same value anymore, coupling constant, but might depend on space. So there's some coupling that takes out of some distribution, and that means we have couplings which are weak and couplings which are strong. And as a result, domains are then trapped, or can be trapped, close to this kind of defects. So what that means is that I showed the very first picture that there was slowing down of the coarsening force. That the domains grow much slower. Okay? And one of the first theoretical treatment of this is due to Hughes and Hanley, and they claimed that okay, in that case the domain should no longer follow power law, but should be a log of time in some exponent. And this was in fact what people believed for many, many years, and the exponent one expect is the psi here is related to the Ruffling exponent, and for the two-dimensional eigenmod should be 1/4. And okay, well, there were some experiments, and some experiments agreed with that, and some experiments didn't agree with that. Now, some experiments in fact showed the algebraic growth law, and Heiko Rieger's group did then a very systematic study on the random bond Ising model, where the bonds are now taken out of this kind of distribution here. You see absolute between 0 and 2, so the value of Gij is between 0 and 2. So you have here a distribution of bonds, and when they look into the growth law, they observe in fact that they do have not an exponential or logarithm growth, but a power law, which a very, let's say, interesting dependence that the exponent Z should depend on the distribution of the disorder and on temperature. And they came up with an explanation which involves that the energy barrier due to the defect is written this way here, whereas in the original theory by Hughes and Hanley, it was given by this way here. Okay, these are details. I think here what is important that they came up with, at least in the time which they could access, that either the logarithm increase or the power law increase. This is of course interesting for us because, as I mentioned all the time, we are interested in this kind of systems. So we looked at this in more detail last year, and this is the correlation function. And you see here the function of T over S, a perfect dynamic scaling behavior for different distributions of the noise and different temperatures. And this is all very beautiful and very nice. We can also look for the response function, and we have a similar very nice and very beautiful behavior. So we have here really, at least in the time which we can access, we do observe the usual dynamic scaling behavior. Now things start be a little bit more complicated when one looks into detail, into the details. What we observe here, this is our computed value of the dynamic exponent, and this would be the prediction by Rieger. Well, it's not so far away, but clearly we do not have the simple 2 plus epsilon over t behavior, but a more complex behavior. So that's one surprise, and in fact right now we do not have a good explanation for that. And the second surprise is that we still have that t is only a function of epsilon over t of the disorder distribution over time. So we have here different points, these are 2 points, corresponding to different combination of epsilon over t, but in the same ratio, and they nicely agree for z, but for a, they do not agree anymore. So we have here that a is not 1 over z. And you recall that I made the case on Friday that due to the interface motion, the exponent a here is related to the dynamic, or to the inverse dynamic exponent. So that basically means that the picture which I sketched, that it is which I sketched is not fulfilled anymore. And this is still a little bit of a question mark, what is the origin of this? One way of dealing with that would be to say that the domains here are the fractal, and that the fractal dimension is modifying this. But this is really one of the many surprises people have when going into disordered systems, and I would not really want to speculate about this in more detail. We can also look at what happens when we have the same ratio epsilon over t and look at the scaling functions. And you see here, the filled symbols are for this combination here, the open symbol of this combination here, and the scaling functions nicely agree. And this is already non-trivial. Okay? So we have different realization of noise at different temperatures, and the scaling functions basically are the same. You not really see systematic deviations. Even more surprising, we have superuniversality. You see, when you look at the scaling function here, you have always appearing the r divided by L over S. So when we express all the lengths by these typical lengths here, and we plot that here, all these data sets, all the scaling functions are identical. And the red one, the green one, is the result for the non-disordered case. That means that, okay, isn't that surprising?
Yeah.
Okay. Well, in fact, this is not really a new claim. It has already been given by Alan Bray and a co-worker some 20 years ago, the first time. In fact, there are now, since 2 years, also some exact results where one can show that it's really only this length scale here which is of importance in coarsening. And if you express every length in terms of this length scale here, then you have a complete data collapse. There are some deviations here, but this is because we need to be in some scaling regime. So we have here something which is super universal. And this should remind you of one of the very first graph I put on Thursday, where I showed you that the original experiment by Struik, measured aging in polymer glass and stuff like that. He had also a super universal scaling function where polymer glass and sugar had the same kind of response to a mechanical force. So there is in aging some kind of super universality which we need to understand a little bit better. We can also look at the space-time response functions, a similar behavior. What is interesting now for our theory is, of course, that, okay, we know how to deal with the perfect case. Now, and when we have the scaling function for the perfect case, we have the scaling function for this order ferromagnet. Okay, and I think I will stop here. I will not discuss the critical significance last because I'm just exactly at my time. It would take me another 10 minutes to discuss that, so we might skip that. If you're interested, we can discuss that in private. Okay, thank you very much.
What's the the insight into this universality? So is this just because you are away from a critical point, you have a certain way of coarsening in this set of models, and you just get out a universal function all the time?
Yes. So the bottom line is that there's only one relevant length scale, which depends on time in this way here. And if we have a coarsening system and we take all the length by this relevant length, time-dependent length here, then the scaling function is the same. So the scaling variables, you have to take the right scaling variables, and the scaling function is independent of the model, of the disorder.
This is also part of my confusion, because at this length scale you do see inhomogeneity in the system, spatial inhomogeneity. But now I'm missing something. So in the original theory, the way you derive the scaling function, there is nowhere you put in this spatial inhomogeneity. You actually claim there is this invariance of...
I'm not sure. Again, what you claim spatial inhomogeneity is not what I claim to be spatial inhomogeneity. I need to have special faculty invariance. It means I should not have a circle somewhere. A real physical circle in my system.
Okay.
Because that will break the theory. Otherwise, what you claim, what you mentioned as a spatial inhomogeneity is included in the theory. Because we have scaling variance. So you can rescale everything and you end up take this scaling variable, you have this included. Okay, is that clear? Further questions?
Now, critical scaling, you also have one characteristic length scale. If you do that in the infinite system, you get super universality.
That's a long story, you know that. So we, of course, also looked at the critical point. And our first claim was, the first paper, that when we plug in the critical exponents, we have a similar kind of behavior. And then my friend Andrea Gambassi with Pascal Calabrese took the whole RG mechanism and decomputed the scaling function to second order. And in first order, everything is fine. Second order, we looked at correction task, which is not included in the theory. And in fact, we then looked closer into the data, and I could identify only comparing numerical data with the scaling variance questions, this question. So, due to randomization, we are losing that. So I do not believe that this works adequately.
So there's something...
But it's still a very good approximation. If you're looking at the data and you compare that, you really need to look very hard to see the deviations, but they are there.
So something special with this, hypothetical zero temperature fixed point that people believe describes cosine, right? It has some very special features which you're kind of identifying.
And again, we know from Letizia Corianto and Alan Bray and co-worker, they have derived some exact results for the Ising model in 2 dimensions and for the disordered Ising model, and they looked at the hull of domains. And they showed really that when you look at the hull of the domains, that the disordered and the perfect Ising model are super universal. That if you plot everything, or if you look at the scaling function, the scaling variable here, all this data, all these exact expressions are the same. Yeah, so we have some exact results which are in agreement with the universality for the 2D disordered parameters.
If you think of this in terms of a flow in some RG space, exponents are the linear stability analysis of the fixed point. And now you're constructing on top of this linear stability plane something like an invariant manifold, which is the nonlinear correction to that fixed point. And if you put it this way, then this invariant manifold doesn't depend on the model.
Yes. And again, there are exact results not by me, but by Letizia and Alan, which show that. Yeah.
I'm sort of confused when I look at that. So you have R over the length scale evaluated at S, but on the vertical scale you have both E and S. Shouldn't there be some dependence on T over S or something?
Yes, it is for. Yeah, I forgot to include that. There should be also S values. Right. There should be also. This is for the same waiting time. This is for a given waiting time. This is given value of S.
This given value of S, but should T come in here somewhere? I mean, you have two times.
Yeah, one second. I have to think. Okay, this is for a fixed value of T over S.
Fixed T over S.
Fixed T over S. Or a fixed value of T over S. Sorry for that. Yes. I should not take pictures out of the publication without being on it. For a fixed value of T over S.
What is the initial condition that you're working from?
Initial condition are in simulation, you mean?
Or whatever.
Well, in any case, we want to prepare the system with short-range correlations. So in the simulation, that basically means we have fully disordered conditions for infinite temperatures.
Some disordered.
Yes. You see, but some people, to some extent, and we did that also, people look into what's going on when you are preparing the system at t equals 0 and then crunching it up. And they are interested only in the crunch up to the critical point. And then you have to take the initial maximization into account, even your numerous dimension, everything into account. But this is well understood. Now, this simulation here, we always start with the fully disordered state.
There's some memory if you put on top of the random initial conditions some kind of spatial structure. Would that remain?
Memory in the sense of memory and data systems?
No initial correlations.
Yeah. So that the system in the final state somehow.
Oh yes, the correlation, sure. So for example, that can be very nicely seen in the spherical model with long-range interactions, initial interactions, long-range initial separation, long-range correlation initial state. One sees that then the exponent scaling functions are changed. So these are the specific separations.
All the best. Okay, everyone's sufficiently puzzled now, so we can mull this over.
There's a lot of stuff here to do. I repeat what Royce was saying. Okay, even though we are not in a steady state, we are relaxing towards an equilibrium steady state. Seems to be very simple. There are many questions.
Well,
okay,
thank you, Michel. And before we check now.